Good day friends, happy Vishwakarma Puja. Today we will be talking on Sindel sequence. Consider the following periodic Sindel sequence 1, 2, 3, 4, 3, 2, 1, 2, 3, 4, 3, 2, 1, 2, 3, 4, 6, 3, 2 and so on. The period sequence 1, 2, 3, 4, 3, 2 is a sequence of numbers whose sum is the modulus m equal to 15. Sum of 1 plus 2 plus 3 plus 4 plus 3 plus 2 is 15. And the period length of the numbers in the sequence is 6. There are 6 numbers in the sequence which repeats forever. A nice property of Sindel sequence is that it is possible to insert in the periodic sequence commas or any other symbol and plus sign so that the visible sums separated by commas from the sequence form the sequence of all positive integers in their normal order. So we start with 1, 2, 3, 4, then 5 is sum of the next two terms in Sindel sequence, 3 plus 2. 6 is 1 plus 2 plus 3, 7 is 4 plus 3, 8 is 2 plus 1 plus 2 plus 3, 9 is 4 plus 3 plus 2. So in this way we can put some commas and the sum of the digits inside the comma form the number sequence starting from 1. That's a very interesting property of Sindel sequence. So I thought about the proof but couldn't prove it. Maybe the way could be the write down the Sindel expansion of the numbers 1 to 15, then 16 to 30, then 31 to 45 and so on. A repeating pattern emerges proving the statement. So let me write down the Sindel expansion of the numbers 1 to 10. 10 is 1 plus 2 plus 3 plus 4, 6, 10. Then go up to 15. Okay, at 50 you get the entire Sindel repeating sequence 1 plus 2 plus 3 plus 4 plus 3 plus 2 which is 15. And this repeating and this sequence, this complete sequence occurs in a pattern. You go to 30, you get 2 of them. And it appears in the other numbers in a pattern. So maybe that will lead to a proof. I don't know the proof. So n equal to 4 is the only solution. Consider the Sindel sequence of the form 1, 2, 3, 4 up to n. Then n minus 1, n minus 2 up to 2. Up to n we get the trivial partitions of the singletons producing the integers 1, 2, 3 up to n. So up to n the partitions are singletons. Then for the next number n plus 1 we need to have n plus 1 equal to n minus 1 plus n minus 2 plus dot 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 plus n minus k. You need the sum k of them, which is nk minus k into k plus 1 by 2 or n into k minus 1 equal to 1 plus k into k plus 1 by 2, and the only solution I see is k is equal to 2 and n equal to 4. So 4 is the only unique solution in the Sindel sequences of the form 1, 2, 3, 4 up to n, then goes down to 2. N equal to 2 also has a similar sequence. The sequence 1, 2, 1, 2, 1, 2 repeating the alternating sequence has the nice property of generating the positive integers 2. 1 equal to 1, 2 equal to 2, 3 equal to 1 plus 2, 4 equal to 1 plus 2 plus 1, 5 equal to 2 plus 1 plus 2. I saw the proof of this. This is easy, but this series 1, 2, 1, 2, 1, 2 also has this property. Some generalizations: for every modulus m is the sum of the numbers. There is a Sindel sequence. It's a well proven mathematical fact. I don't have the proof. For example, for m equal to 17, the sequence will be 1, 1, 1, 1, 2, 4, 1, 4, 2. 6, 7, 11, 13 plus 4, 17. The sum is 17. For m equal to 19, the period sequence is 1, 1, 1, 3, 1, 2, 1, 5, 2, 2, 4, 9, 10, 12, 13, 16, and 3, 19. There are nice arithmetic problems related to those sequences, most of them using a triangular number. If you look at the partial sums of the Sindel sequence, they form the triangular numbers. But it has the property too, with different partitioning, we can generate all the integers starting from 1, 2, etc. The clock of Prague, the Sindel sequence is used in gearing of the Prague astronomical clock as part of a mechanism for chiming the clock's bells and correct number of times at each hour. The Sindel sequences are named after Jan Sindel, a Czech scientist in the 14th to 15th centuries, whose calculations were used in the design of Prague clock. So the sequence originated in 14th or 15th century, which is 1100 years till today, and the clock is still running. The definition and the name of these sequences were given by Michael Kriek, Elena Solkova, and Lawrence Sommer in their work analyzing the mathematics of Prague clock. So Prague clock is still there. References: I took content from Wikipedia, and then I also took content from Stack Exchange, and a talk by Professor Ashok Mollik initiated this idea in me. Thank you. Like, comment, share, subscribe. I am available for one-to-one sessions too. Thank you.